This is our last section of Chapter 1, the second section of our math review. And we're going to start our discussion with measurement. What's the measurement? Measurement is the quantitative observation. That means we record our observation with the numbers and, of course, unit, as we discussed the last time. When we write down the value, there's two rules or criteria that we need to be aware of. Because we just cannot write whatever the value we want. Not only we have to write down value that is shown or through our measurement, shown by a device or in our measurement, and also there's two rules that we have to follow. First, precision. Okay. We need to worry about just how close our measurements are to each other. And second criteria that we need to worry about here is accuracy. It means just how close our measurement to the real or true value. That is also equally important. In my view, that accuracy is probably more important than the precision. But being a scientist, what I can tell you at this moment is in the real world, it is a precision that is more important than accuracy. Because precision is what we call the reproducibility. That means whether we can repeat our measurement again. Because if we cannot repeat our measurement again, that definitely going to cause the problem in making people believe your result. So we have just talked about the two criteria that we need to be aware when we measure our experiment. So here, what I'd like to use the dart and the dartboard to represent these two almost equally important criteria in our measurement. The bullseye right in the middle here is the real or true value. And those locations of a dart are our measurements. When we do measurement, we always do like a 3 or 4 at least in order to make sure that the precision is good, because we want at least those measurements can stay very close to themselves. Apparently, the first one is not good. Not good in either precision nor accuracy, because those spots are very much spread out and they all shift in one direction, not in the bullseye. So that is poor in both. What about our second? Our second, however, it is quite obviously, we see it is a poor precision because they all spread out. Those spots are not close to each other. What about the accuracy then? Is accuracy as bad as it looks? When we look at these two spots, and if we take a line between them by taking the average, we suddenly realize, hey, this is where the average is, right in the bullseye. For these two, if we take the straight line to it and half of this, taking the average, we realize that's also in the bullseye. That means the accuracy actually is pretty good. But how confident are we to believing such measurement? Because we got a measurement all over the place. Even though the result shows the precision or the accuracy is good, but it might be just a lucky shot, right? So we do not have much of a confidence in such a measurement. So that is the problem. That is why I say in the real world, we look more on precision than accuracy itself, because we just want to know our measurement at least to have certain degree of a confidence for us to believe in. All right. The third case here, of course, you see the measurement are very close to themselves. The precision is good, but the accuracy is off. This kind of measurement can be corrected. No problem. All we have to do is calibrate our device. If we have a scale, and then calibrate the scale. If you have a ruler that is not good, get another ruler, right? So all of this poor accuracy stuff can be corrected. And of course, last case is good in both. That is the one we want when we take the measurement of our experiment. Okay, the last two are the ones I want you guys to focus on a little bit, okay? Because good precision does not necessarily means that we will have a good accuracy. So this is something that I want you guys to keep in mind for a few minutes. Now let's take a measurement. Take a measurement of temperature. Okay, so with this thermometer, we realize that the temperature is somewhere between 30 to 35 degrees, right? And of course, as we blow it up, we realize that the tip of this mercury column actually goes somewhere between 32 and 33. Many people probably think it is safe for us to report 32 degrees. I have no question about it. Yes, 32 degrees is a safe bet. But the writing 32 make us miss one important point. The temperature is between 32 and 33. When we just write down 32, and then I can guarantee you everyone can read a 32 from the thermometer, that means the precision is good. What about the accuracy? Because that 32 does not tell or does not give us any information about what is really going on for this temperature, right? The temperature is between 32 and 33, but none of these measurements showing that point. I hope you guys understand what I'm trying to say here. Remember, precision is good, but accuracy is equally important. We need not only our measurement is precisely enough, we also want our result is accurate enough. What is the accuracy about our reading on the temperature with this thermometer? I'd like to say, since the temperature is between 32 and 33, I would like to put up a one additional digit to say it's a 32 point something. And also I can estimate the temperature is between 32 and 35 on the lower end. It doesn't reach the half of that degree yet. So I'd like to say, how about 32.3? Do I have absolute confidence in that the 0.3 I just made? No. Do do I have absolute certainty with that 0.3 I just claimed? No. All I want to let people to understand here is the temperature is not only 32, it is a 32 and 33. It's between 32 and 33. And it's on the lower end of the 32. To a 32. So that's a 32.3. That is what I estimate. I just wanted to reach the point. The temperature is between 32 and 33 on the lower end. So that 0.3 is an estimate value. Maybe somebody will read like a 32.4. Somebody will read, well, I kind of disagree with your statement about 0.3. I believe it's right in the middle, so I would like to put it 32.5. I would hold no argument. Because that number is just trying to make a point, the temperature at least between 32 and 33. Can this argument go away if we have a better thermometer? So say, what happens if I find a way to make this 0.3 absolutely sure? Well, let's see. Now we have another thermometer, much better thermometer. Okay, so for the same temperature as we measure this time, as we see here, it's between 32 and 33, no doubt. And also we can read that is a 32.1, 32.2, 32.3. Now we have a 32.3 for sure. Seems like we just get this problem solved, right? Now with the cheaper thermometer, we have to estimate 1 decimal place to let people to understand that there's 32 and 33, the temperature between the two. And now with the better thermometer, everybody knows it's a 32.3. The temperature is between 32 and 33. But what we do see here, again, is between 32.3 and 32.4 again. Do we have to estimate? Yes, we do. Because based on the same argument, we need to let people to understand or give people more information about this temperature is somewhere between 32.3 and 32.4. By following that argument we just had before, we need to make one more digit to let people to understand the temperature is between 32.3 and 32.4. So it seems like this estimation does not go away even with a much better device. It could always be in a situation like this, something right in the middle of the two marks. All right. Now we just realize that our last digit could come from our estimation. Since it's our estimation, we call that digit uncertain. If we do have a digital measurement device like a digital balance, and sometimes you probably see the last digits keep fluctuating. Like every time when I go on the scale, try to watch my weight, and I see the last digit keep fluctuating. That is also we call inexactness. So if we have inexactness of our measurement from the digital device, or the necessity of estimating from the thermometers, as we just discussed, all of those give us a uncertain digit, because that digit is subject to change if we have a different guy to conduct the same experiment. All right. The number of digits, or where this uncertain digit is located, is totally depend on the device. In other words, with the better device, we're going to have more digits to write up. If we have a cheaper one, we're going to have a less number of digits to write down in our measurement. So that is why in the sophomore level of chemistry major, we have a class, and we're going to reinstate this uncertainty and also provide a guideline just so what kind of number of digits is sufficient to support us to conduct the experiment without costing too much. Because I like to say the one on the left, the better thermometer, usually is about 20 times more expensive than the one on the right. So we need to make our judgment to see just which device is sufficient enough to give us the numbers for our measurement. All right. So now that we have established that we can have our last digit from our estimation and or inexactness of a measurement, and we call it uncertain digit. And there's a rule about it. The rule says uncertainty is always lied in the last digit. With this rule, we cannot write the string number as many digits as we want, because we need to be responsible and we need to let the people to know, okay, just what is our last digit should be, because that last digit is uncertain. All we need is just one uncertain digit. There's no need for us to get a 2, because if I have a first digit is uncertain, the next digit, of course, is uncertain. It doesn't make any sense to write up 2 uncertain digits for our measurement. So the rules states uncertainty always lies in the last digit. I want you guys to keep that in mind. Okay, any digits that is on the left of the uncertain digit is what we call certain digits. That means those digits we measured with 100% of confidence from the device. If the device is faulty, that's a different story. Okay. So we have certain digits and we have uncertain digit. The more the digit we write down indicates the better the certainty that we have, also indicates the better the precision. So be careful from this moment on when you write down the numbers in your lab report. You cannot give me like 6 digits in your measurement, because I would ask you just what instrument can give you this many digits, because I know for sure our lab cannot give you that kind of accuracy or precision. So be very careful from this moment on when you write down the numbers in your lab. All right, so since writing down numbers is very important because remember our last digit is always uncertain, so we can have a concept called the significant figures or significant digits. That means the numbers we write down on the paper in our lab report are significant. We cannot afford to miss any one of those. Okay, so significant figures include all certain plus one uncertain digit we recorded in our measurement. Why is that so important? Because our calculation is based on the significant figures. We're going to use that concept to guide us to carry out the certain calculations. And of course, there are rules for this. Just how we're going to determine or count the number of sig figs, short for significant figures. Basically, all the non-zero digits showing up in our lab report should be considered as significant because by the rule, right? So we just give whoever does the experiment 100% of credit. They say they know what this rule is all about. They know it, they follow it, so this is the number they have, and we just trust the value. If they give 5 digits, okay, so all these 5 non-zero digits should be considered as a significant. In our case, 137, there are 3 significant figures. Our certain digit of 7. Remember, it's always the last one. Because there's no reason for us to take one off, right? All of them are significant. But when we have zeros, however, things become a little bit more complicated. Interior zeros are the zeros that's between the 2 non-zero digits, like 0 and 1.037. I'd like to remind you the last digit is uncertain, so that the digit of 7 here is uncertain. If the digit 7 is uncertain, since 0 is on the left, making this 0 certain. In other words, interior 0 is significant. We need to count that 0 as the significant figures. Therefore, 1.037 has 4 significant figures. What about the leading zeros? Leading zeros are the zeros in front of our first non-zero digit, like 0.0043. How many significant figures are there in this number? Should we consider this number with 5 significant figures? Because 0.0043, right? 5 digits. Should we consider that as a 5 significant figures? I also recall that many people would call this number as 0.0043. Or that'd be 4 significant figures then. And then I can continue arguing. Since the first 0 before the decimal point can be ignored, making that 0 not significant, what about any other zeros? What about the other 2 zeros? Are they significant enough for us to call it? So with all this kind of argument, people finally realize that we just do not count those leading zeros. In other words, leading zeros are not significant. In the words of my former student, those zeros are just placeholders to tell us how small the value is. They are not significant because we can make those zeros to go away. If we can make those zeros to go away, those zeros are no longer significant. So just how many significant figures do we have from this value? 0.0043. Only 2. Now, what about the trailing zeros? Trailing zeros are a little bit more complicated. Trailing zeros in my class, okay, I just want to make sure that in my class, I would take those zeros as ambiguous. Why? Because since those zeros, after those non-zero digits, we just don't know how many significant, how good or significant for any of these zeros. For example, 5,300. I just don't know how many significant figures can I have in that value. Could it be 2, just a 5 and 3? Could it be 3, 5, 3, and the first 0? Or could it be all 4 digits? I just simply don't know. But things are going to change if we have a decimal point present in the number. Say if I have a 5,300 point. Once this point, decimal point shows up, all the zeros are significant. The reason for people to put the decimal point there to let everybody understand that we're going to treat those trailing zeros significant. We cannot miss or ignore any of these zeros. It doesn't matter whether there's going to be 5,300 point or 530.0, it doesn't matter. As long as we see the decimal point there, all the zeros, all the trailing zeros, the zeros that are after non-zero digit are significant, period. No argument. So that is why, remember that statement, trailing zeros are only significant when a decimal point is present. Without the decimal point, we just simply do not know how we are going to treat those trailing zeros. I will treat none of these zeros, or some of the zeros, or all of those zeros. We just simply don't know. In order to clarify that argument, remember that we have some cases like we are not going to count those zeros, or in some cases that we do not know, we need a clarification. In order to clarify this, we proposed a notation we call scientific notation. It has 2 parts as we see, A, and second part 10 to the x power. The first part we call decimal part. Decimal part must be a number that's between 1 and 10. The only function for that part is we know just how many sig figs in our value. You may wonder what happened for the leading zero, because leading zeros are not allowed to be the decimal part. The number must be between 1 and 10. What happened if we have a trailing zero? Trailing zero, because their decimal point is there, trailing zero should be counted as the significant figures. So, according to scientific notation, we do not have any problem with those leading zeros or trailing zeros anymore. All all the numbers written in the decimal part of the scientific notation is significant. As for second part, exponent of this exponential 10 to the x power, it just let us to know just how big or how small the number is. If x is a positive, that means we need to multiply this number by 10 to the x power. If the exponent is negative, that means the value is small. We're going to divide this value by 10 to the x power. It's just as simple as this. So scientific notation only deals with the number that's either too big or too small, that people may have confusing or maybe confused about the significance the measurement actually has. All right, so just how we're going to convert our scientific notation to normal notation, like a 4.3 times 10 to the negative third. I believe many of you guys will realize it's a 10 to the negative third. That means 4.3 divided by 1,000. So what we have here is 0.0043. According to this approach, we're going to move our decimal point to the right if the exponent is greater than 0, and we move our decimal point to the left if the exponent is less than 0. In other words, 1 is divided, so multiply by whatever the multiple is, and if it's negative exponent, that means we're going to divide it by. But I don't know if you just realized or not. The result here is 0.0043. And its a scientific notation is a 4.3 times 10 to the negative third. Interesting thing here. How many significant figures do we read from that 0.0043? It has to be 2, because 4.3 from its scientific notation shows there are only 2 significant figures. That proves that leading zeros are never counted as significant figures. I just want you guys to keep saying this until it becomes part of your life, as long as you take chemistry classes. Okay, so what about if we want to convert some very large value or very small value into a scientific notation? First step, we obtain a number between 1 and 10. For example, if we have a 5,983, we're going to move the decimal point 3 times to the left to make it a 5.983, because that is the value between 1 and 10. Then we're going to compensate that value by certain factor, because every time when we move the decimal point, we either increase the value or decrease the value by the factor of 10. Since we move our decimal point 3 times to the left, every time when we move, we decrease the value by the factor of 10. 3 times means we decrease the value by 1,000. In order to compensate this, so we multiply by 10 to the third. Sometimes more to make sure that's a 5,983, not any other numbers. So x is equal to number of movement of decimal place. X should be positive if we move our decimal place to the left this time, when we try to decrease the value in order to obtain the number that's between 1 and 10. On the other hand, if we have to move our decimal point sometimes to the right in order to obtain the decimal part, exponent must be negative, because we move a decimal point to the right, we increase the value by the factor of 10. every time when we move it. And of course, this is another example for us to realize that we do not have to count leading zeros. And I have already emphasized 3 times about how we treat leading zeros. I just want you guys to remember it, because that could be a very good question in our exam. What about those trailing zeros? Now we realize we can have 3 scientific notations to represent that of 5300. We can have a 5.3 times 10 to the third. If we do not worry about decimal point, 5.30 times 10 to the third, 5.300 times 10 to the third, they all give us a 5300. 5.3, how many same things? 2. 5.30, 3. 5.300, 4. So that is the reason why trailing zeros without the decimal point is ambiguous as the best. There are a group of a number that, alright, there are certain rules about how we're going to perform our calculation with the significant figures. The first rule here is about addition and subtraction. For addition here, when we perform addition, our result should have the same number of decimal places as the quantity with the fewest decimal place. In short, we are looking for the decimal place. We're looking for the least decimal place. For example here, we try to add these 3 numbers together. After we punch those numbers in our calculator, we have a 9.214. Just how many digits should we pick here as we report? Is 9.214, those 4 digits, good enough for us to report, or should we just take some of the digits off? Remember here, our results should have the fewest decimal place, right? So let's count. 2.74, how many decimal place? 2. 0.823, how many decimal place? 3. 2.651, 3. How many decimal place do we expect in our answer? Remember, fewest decimal place. 233, 2. So which number should be our last digit? 1. That means 1 should be the last digit for us to report. All right. Why? Why do we have to count decimal place instead of counting significant figures? All right, so let's try it out this way. Like we are the 7-year-old. Okay. Try to do the math without a calculator. So as we lay out those numbers all together, and we find out the sum is 8.214 here. Remember, okay, just how remember last digit of each quantity represent uncertainty, right? Uncertain digit. So 0.823. We understand that 3 is uncertain. 2.651, that digit of 1 is uncertain. That makes that 4, digit of 4, uncertain. Does that make sense? When we say uncertainty, that means that number can be changed a little bit. Some people will say 3 is not good. I'd like to make it a 4 or make it a 2 because it's uncertain. Nobody will argue with that. So I just want you guys to understand, for uncertain digit, that means that number, that digit could change that value a little bit. If I change the value from 3, from that 3 to 2, 4 is not going to be good anymore, right? 2 plus 1, that would be 3. So that means we got 4 uncertain. All right? So we got the digit of 4 uncertain. What about the 5.74? Which one's our uncertain digit? Here. 4 is uncertain. That means 4 can be switched with 5, for example. If we have a 4 switched with a 5, we understand that that 1 is no longer good. Right? If we switch a 4 with a 5, that 1 should be 2. What does that mean? It means that 1 is also uncertain because one of these 3 digits, when we do the addition here, is uncertain. Even though the other 2 are certain. But since 1 is uncertain, it becomes uncertain. Kind of like a bad apple in a pile of a good apple. So we realize that the sum 8.214 has 2 uncertain digits. Remember, we only pick 1. So that is the reason why we look for the fewest decimal place in our addition. All right. So the number we should have stopped at is the digit of 1 in our addition. What are we going to do with the 4? We round it off because 5 is a whole number. Okay, 5 or higher, we round it up. 5, 4 or lower or smaller, we round it down. That rule also applies to the subtraction. And before we do the subtraction, I just hope that you will understand what this cartoon is all about. All right. So here's the lady telling her friend that this dinosaur bone was 65,023 years old. And her friend puzzled and asked, "How do you know that?" Well, okay, so this lady said, it was dated as being 65 million years old, and I got it 23 years ago. So I added that 23 years on top of the 65 million years to make the 65 million and 23 years. I hope you get it. The point is, how significant do you think that 23 years is compared to 65 million years? Okay. So this cartoon actually tells us when we try to add the 2 numbers together, we're looking for the fewer decimal place. As we said, the subtraction follows the same rule. If we have a 14.8 minus 3.965, our calculator shows a 10.835. Now, to what digit should we stop counting? Remember, subtraction fewest decimal place. This one got only 1, so we stop at first decimal place. And the next digit 3, less than 5, we round it down, so we have 10.8 to report. Again, I want you guys to be very careful when you perform calculation with a sig fix. Okay, addition, subtraction, we're looking for decimal place. For multiplication and division, we are looking for the fewest sig fix. So for example, we got the 3 numbers multiplying all together, punching those numbers in the calculator, it shows 45.0118. All right, how many sig fix should we keep here? Remember, we are looking for the fewest sig fix, right? So 5.02, how many sig fix do you think we have here? 0 in the middle, we call it interior 0. It is significant. So we have 3 sig fix in this number. All non-zero values should be counted as significant, so we got a 5. The question is, how many sig fix do we read from our last factor? Should we count this leading 0? No. Should we count this trailing 0? Yes. Why? There's the decimal point. So we got a 2 sig fix in our third factor. Remember, our result must have a fewest sig fix. 352, 2 is few. So we count from left, 1, 2. We stop at the digit of 5 for sig fix. And we round it down the rest, so we just simply call it 45. Division follows the same rule here. 5.892, that's a 4. And 3.10, how many significant figures? Trailing zeros with decimal point, it should be counted, right? So we got 3. Okay. To which digit should we count our sig fix? Should we start from 0 or start from digit of 9 for 3 sig fix? Remember, leading zeros are not counted, right? So we cross that out. Start with 9, 6, stop at digit of 5. Since next digit 9 is greater than 5, so we round it up, so we report it as 0.966 miles per hour. Remember, we got the units. Units can be divided, so we have, meters per hour. Meters divided by hour, so we have meters per hour. All right. Seems like a multiplication and division is quite straightforward, right? So we're looking for the fewest sig fix from the factor. So how about addition and subtraction? Can we get a sig fix directly like we have in multiplication division? No. Just keep in mind, when we finish addition and subtraction, we determine decimal place before we count sig fix. It is critical. We determine decimal place before we count significant figures in our result. All right, speaking of the rounding, as we already discussed, if we have the digit that is about to remove that's greater than or equals to 5, we round it up. If we have a digit that we want to remove less than 5, we round it down. And of course, our textbook is a lot more complicated than that, and I really don't think we need to take that rule. If you are just happen in the chemistry major, and then you all get straightened out later on in other chemistry classes. So I really don't think we have to follow that rule for general chemistry. So just follow mine. Mine is good enough. And our real challenge here is to perform mixed calculation with the significant figures, like converting temperatures with the 3 different scales. We got addition, subtraction, we got division and multiplication. When we perform that kind of calculation, I want you guys to keep in mind we count both. We count both sig figs and decimal place in every step of a calculation. We'll start from very first step 1. And we're going to do that to the end of calculation. For example, we got this thing going on. Alright, we got addition on top, multiplication, division on the bottom, and we punch those numbers in our calculator, so this is what we have. And 25.65 plus 37 plus 4, so we have 63.05. And 73.55 multiplied by 1 divided by 60, and just pick enough digit for us to choose. All right. Let's see. The numbers on the top is addition. What do we have to count? We count decimal place or sig figs? You're right, we count decimal place. 25.65, 2 decimal place. And 33.4, 1 decimal place. So where should we end? Digit of 0 here. By stop counting at the digit of 0, we realize there's a 1 decimal place. And how many sig figs? 1, 2, 3. Because 5 is out. 5 should be out later. So we know we need 1 decimal place, 3 sig figs from that 63.05. When we try to count just how many sig figs for the numbers at the bottom, we realize there's a conversion going on between minutes and second. And one value is 1 and the other is 60. Does that necessarily means that 1 has only 1 sig fig and 60 has, I don't know, because it's a trailing 0 without decimal point, right? So how can we make a decision? And I just want to remind you that it's conversion between the 2 different units. 1 minute equals to 60 seconds. Can we change any one of these values? Say, can I change 1 minute to 2 minutes? Say, 2 minutes equals 60 seconds, or 1 minute equals to 61 seconds? Of course not. Since we cannot change the value of either one, we treat both values as exact numbers. Since they are exact numbers, we don't care the sig figs for them anymore. All we have to do is count how many sig figs we have from 73.55. There's 4 sig figs. As we count, the sig fig should stop at the digit of 5. That means 4 sig figs, how many decimal place? 1, 2, 3, 3 decimal place. Why do we have to do all of this? Because we just simply don't know what is next. If it is the division or multiplication that's next, we're going to rely on the sig figs. If we have addition, subtraction next, we're going to rely on the decimal place. That is the reason why we have to count both. If you think that is complicated enough, wait to see what we have in our textbook. Because in our textbook, it says we should keep one more digit for the sake of accuracy when we perform the next step of calculation. So that means we should keep that 5 and 8 for our next step of calculation. All right? Have that being said, let's look at what is our next step of calculation. It's a division. Division, we rely on sig figs. The field is the sig figs, right? So the one on the top, as we said, 3 sig figs. The one at the bottom, 4 sig figs. How many sig figs do we expect in our answer? 3. Let's punch those two numbers in our calculator and find out. Remember, our answer should have 3 sig figs because it's our final answer. So that should be 51.4 milliliters per minute. Why did I put this parentheses around? Because what I'm about to do here is pretty much unorthodox, but I think they are very practical, and it's going to save us a lot of effort and time when we deal with this line of calculation. So I'm going to change the rule of calculation a little bit. The rule says we're going to keep one more digit. What I'm about to say here is, no, we don't. We round our result before starting our next step of calculation. Why? Because that makes our life much easier. All right, so I do not have to keep that the digit of 5 and 8. What am I going to do? I'm going to round them up because 5 is 5 for round up. 8 is greater than 5 for round up, right? So let's just simply round them up. So what we got here is a 63.1 milliliter divided by 1.226 minute. What do we have here? Remember, we are looking for a sig figs, right? So 63.1 has 3. So our answer should be 3. That's a 51.5 milliliters per minute. Any difference? For mathematics, yeah, there is, right? 51.5 is different from 51.4. But I'd like to remind you we are in a chemistry class. We have just talked about uncertainty. Now tell me, which digit is uncertain? From 51.5, last digit, that 5 is uncertain. 51.4, that digit of 4 is uncertain. Now you tell me how much the difference do these two numbers make? None. None whatsoever. Because they both are uncertain digits, subject to change a little bit, right? So in chemistry, 51.4 and 51.5, no difference. So now I just want you guys to understand, okay, so we change this procedure a little bit. We round our result before we conduct next step of calculation. That makes our life much easier. Okay. It may not show too much in this example, but imagine if we got 2 or 3 more steps to do. And we have to keep tracking, okay, so how many decimal places, how many sig figs, and plus 1 more digit. And I knew that feeling. Okay, I was there before. Took me a while to get used to. And why do I have to do that? Because I was a chemistry student. So I will go easy on you guys. So to make sure, so you guys just have to make sure that you run the result with the correct sig figs before you perform the next step of calculation. All right, so now let's see. This line of question probably going to show up in our homework assignment as well as in exam. Okay, So it says perform the following calculation and round the answer to the correct number of significant figures. I just want you guys to take an educated guess. How many sig figs do we expect from this calculation? 4, 3, or maybe 2? Does anybody think of 1 sig fig in the answer? Let's see. Remember, the rules of calculation tells us we do everything inside the parentheses first, right? So we do the multiplication first on the top, division at the bottom. Multiplication, division, we're looking for fewest sig figs. We got 4, 4, 4, 4. They are 4 sig figs. All right, make it easy. And remember, I just round to the appropriate number of sig figs in our values. The multiplication leads us 5.952. The division leads me 0.2392. Both have 4 sig figs. Now, there are extra step on the top, which is subtraction. When we do subtraction, we are looking for your right decimal place, right? So our first quantity has 3, and our second has 2. Our answer should have, yes, 2 decimal place. 1, 2, 2 decimal place. But our first decimal place is what? 0. That makes how many sig figs in this number? Only 1. So 2 numbers divide, you're looking for the least sig fig. We wind up with -0.1. Only 1 significant figure in our calculation, right? In our answer. So I just want you guys to do this calculation before you call for the number of sig figs in our answer, because things can change dramatically. What is wrong with this? If we have a 5.98 divided by 2.47 times 10 to the second, why can't we just type those values in our calculator as this? 5.98 divided by 2.47 times 10 raised to the second power. Why? That is because, according to the values from the left, that should be 5.98 divided by 247, right? Because scientific notation tells us it is 247. Unlike the one right here, by typing those numbers in our calculator, the calculator recognizes it's a 5.98 divided by 2.47, then times 100. It is not 247. So that is the reason why it will give us the wrong result. How can we correct this? You're right, we put parentheses around to let the calculator realize it's going to perform a calculation first to get to 247 before it carries out the division. Or if you have a TI calculator, you probably find there's a double E key in our calculator. That double E key tells us the calculator is ready for scientific notation. Therefore, what we can do is we type 5.98 divided by 2.47, hit that double E key. Sometimes you have to hit second key before you hit that key to get this E showing on the screen. Once the E showing on the screen, it says the calculator is ready for scientific notation. 10 to the second, So we put 2 in there to let calculator realize it's a 2.47 times 10 to the second. All right, our last example. What do we get when you quadruple 21.72? Of course, quadruple means 4, right? So 21 times 21.72 times 4. Now we have a decision to make. 21.72, 4 sig figs, 4. Seems like it has only 1 sig fig. So which one should we pick? 86.88 or 9 times 10 the first? Sometimes we should be alert about a simple number like 4. Why 4? Why it has only 1 sig fig? Does it come from somewhere, like a definition? Where's the 4 come from? Quadruple. Quadruple means 4. Can quadruple means 5? No, of course not. That makes 4, that digit 4, what? Exact number. So once we realize it's the exact number, we do not have to care about it. It's sig fig, 21.72, 4 sig figs. We report 86.88 with a correct number of sig figs. All right, so that is what I like to have to say about the significant figures. When we perform this line of calculation, we need to be very careful. We need to be very careful about how we're going to count the significant figures when we calculate. But for the rest of these courses, we do not have to use those rules unless we are instructed. Unless we say, watch the sig figs when you calculate. Otherwise, just use your common sense. 2, maybe 3, maybe 4 digits will be good enough. But it can never be only 1 digit. So for example, if questions ask only 1 sig fig, okay. So if you only give me 1 sig fig, if a result is a 0.56, what are you going to give me? 1 instead of a 0.5, that makes a whole lot difference. Okay? So make sure that you give me at least 2 digits when you calculate. But also I want you guys to understand and memorize those rules on significant figures, because that is a part of curriculum and we are going to get it tested one way or the other. The last physical dimension I like to have a little bit of discussion is density. Density, according to its definition, is a mass per unit of volume. And the mathematics tells us it's a D, small case letter D stands for density, equals to M, which is a mass over volume. I just want you guys to get used to those symbols. Those symbols actually represent those physical quantities. And we cannot change, okay, those D or M into the capitalized form because they very much mean something different if they are capitalized. Okay, so density must have the small case d, mass must have a small case m. Density is an intensive property. Okay? It is a physical property because when we talk about density of something, that substance does not have to change its chemical identity. So that's a physical property, and we know it has nothing to do with the size and the volume or the amount of the substance. Remember we said that before. As long as it's gold, no matter how small, how big the chunk is, they have the same density. But in chemistry class, another function of density is to use as a conversion factor for unit analysis, or somebody would call it dimensional analysis. The reason for that is the density shows up the ratio of quantities in different physical dimensions. For example, density of mercury, 13.6 grams per cubic centimeter. Remember, gram is a unit of a mass. Gram is a unit of a mass. Cubic centimeter is a unit of volume. So we are talking about a conversion factor, the factor that connects the value of two dimensions together. And that becomes quite important when we discuss the dimensional analysis or unit analysis later. But I just want to give you guys a heads up. All right. Now let's look at our last example problem. All right, so in our lab, someone wants to determine the identity of the unknown liquid. And it could be one of the three. Ethanol density was this much grams per milliliter, or chloroform 1.48 grams per milliliter, or water, which is 1.00 grams per milliliter. So how does the experiment be performed? We use a graduate cylinder and we weigh down the balance while it's empty. So we have 38.751 grams. And we add certain volume of liquid in, and we find that the volume is 10.1 milliliter. And with that liquid, graduate cylinder now has a new weight or new mass, 53.502 grams. What about the identity of the unknown? When we perform the calculation problem, I just want you guys to realize there's a certain procedures that we're going to follow. And follow those procedures will make your studying chemistry much, much easier. Okay. First step in that procedure is organize information. I have been doing this since I was a 5th grader. This is how I got trained. Okay. It is almost 45 years, and I'm still doing it because organize information in your own way make your calculation much, much easier, because once you're done organizing information, you do not have to read all these words in a problem. This is my way to organize information because I know the mass, so I use M to represent the mass. I use subscript to identify what kind of mass that one is. Cylinder, so that means the empty cylinder. And the mass of cylinder plus liquid, so that's the new mass. The volume, 10.1 milliliter. What is question 1? Question 1 is the density. What's the unit of density that we have in mind? Check out the densities of these 3 liquids. They all have grams per milliliter. So I'm going to use gram per milliliter so that I can simply compare the values instead of worrying about whether we have to convert even further about the unit of density. Now I'm going to use gram per milliliter. First step, I need to figure out the mass of the liquid by subtracting these two numbers together. And what I got here is 14.751. Remember, for both of these values, they have 3 decimal places, so that's why our answer should have 3 decimal places. And what are we going to do next? If we do not know what we're going to do, we lay out the unit. Remember, the unit is gram over milliliter. What is the number that goes along with the gram? 14.751. What is the value that goes along with the milliliter? Here we go, 10.1. So that's why we put numbers in the position so we know just what kind of calculation that is going to be ahead. One thing I want you guys to keep in mind, number and unit are never separated. They go together. All right, so as for density, which is the mass divided by volume, so we have a mass divided by volume, it's 1.47 grams per milliliter. Which liquid do we think that this one is? You get it? Chloroform. That is the end for the chapter 1. Okay, so in chapter 1, we divided it into 3 sections. The first section, okay, so there's the first of 4 aspects of chemistry that we have discussed: composition, structure, property, and what is the 4th one? Change, right? And then we did the first half of the math review in 2 sections. We focused on the units and the physical quantities in our first section of a math overview, and we focused on the numbers. How do we write down numbers in this section? And I thank you for your time, and I see you guys in the next chapter. Thank you.